my name is Sato, and today I'm going to be walking us through a quantitative physics force problem. We're going to use the problem-solving guideline, and I'm just going to walk you through it step by step in easy bits. So let's begin. You're carrying two boxes, one on top of the other, into your building. To open the door to the building, you hold the 8 kg box, box 1, against the wall next to the door by pressing one hand perpendicularly to the side of the box opposite the wall. Stacked on top of the box you're holding is a 4 kg smaller box. We're going to call that box 2. That's not in contact with the wall. If the coefficient of static friction between box 1 and the wall is 0.80, what minimum magnitude of force in pounds do you need to apply to box 1 so that nothing moves? And in this problem, we already have our answer, so by the end of it, that is what we should get. Okay, so the first step in our problem-solving guideline is to define the concepts. So we're going to say concept. Say it's frictional forces. Ooh, I did not write. And force pairs. These are two concepts that this problem focuses on. Okay, the second step in our problem-solving guideline is to write down all the given information and or any hidden information. So given, the problem tells us that the mass of the first block, the bigger block, so we're going to say that's M1, is equal to 8 kilograms. And M2, the smaller box that is on top of mass 1, is going to be half that at 4 kilograms. Also in the problem, it tells us the coefficient of static friction, so mu sub s, is equal to 0.8. That doesn't say, it's a unitless term. And so, what else do we know? So we know that the acceleration in the y direction is going to be 9.8 meters, so let's define that as ay, because in the y direction, so ay is equal to 9.8 meters per second squared. And then ax in the horizontal direction, we know it's not moving in the horizontal direction, so we're going to define ax as 0. Don't forget your units. Units are very important. So from there, we're going to think about it like, so if it's not moving in the horizontal direction, the whole system isn't moving, right? We're going to define it as the sum of forces, right, is equal to mass times acceleration. The acceleration, because it's not moving at all, we're going to say that F, sum of forces, is equal to 0. Okay, that is all of our given information. The next step in our problem-solving guideline is to write down any assumptions we have. So we're going to assume constant acceleration, and no error. So we're in happy physics land here. There's no error resistance. Okay, so the next step in our problem-solving guideline is to define what the question is asking for. So the need. So what's the need? What are we looking for? So need. We're looking for the force exerted by the hand on the system in, and this is where we're going to have our units. So the question wanted it in pounds. LBs. Or, now we've defined, any assumptions we have, what we're looking for in the problem, and now we're going to make a prediction. So based on any of the given information, we can assume that the force that's going to be exerted, so we're going to do predictions. Let's say between 10 and 100 pounds of force by hand on the system. Okay. So earlier I had erased our given information, but I rewrote it again. So the next step is for us to draw a picture of our scenario based on our information. So first I'm going to draw a general picture, and then I'm going to draw a force diagram. So let's do, so I'm going to call this the wall. We're going to draw mass 1, right? It's the bigger box on the bottom, it's 8 kilograms, and then mass 2, which is another box, not touching the wall, but is on top of mass 1, smaller box. And then we have a hand, right? Because I'm not an artist, I can't draw a hand, I'm just going to draw an arrow. So it's the hand that's pushing the box into the wall, and then the wall is pushing back on it, so nothing's moving. So this is our general picture. So now I'm going to draw, first let's define our system, right? Our system is going to be box 1 and box 2. Just okay, mass 1 and mass 2. Okay, so let's do this. So I'm just going to draw that circular point. It's going to be our system, right? And we're going to say that there is a force on the system, right, the Earth. So F, system, Earth, right? Force, system, Earth. That's how you have to write it, right? We're going to force on body, right? Then we're also going to have, oops, that's not a straight line. Oh, let's just erase that. Okay, and it's going to be upward, right? It's going to be the same length as the other thing because it's not moving in this direction. It's going to be force on system, right? But then, because, what's the reason that this thing isn't moving, right? It's the static friction, right? Because I'm holding it against the thing. What's preventing it from going up and down? We know that the Earth is, pulling everything down, gravity. But here, what's keeping it from going that direction is the force of friction. So we're going to call this force on system by the wall, so the friction of the wall. So we're going to call this like static friction. Just call it that. That's what we'll do. Right? And these are the same size because nothing's moving, right? We also here have a force on the system by the hand, by the wall. It's always opposite, by the wall. Call that. That's also our force normal. Okay. We also have in the opposite direction. Ooh, that's very bad. Force on the system, so F sub S by the hand, so H. F sub SH. I didn't draw that very clearly, but that's what it is. Okay, cool. These, because nothing is moving in the system, right? The hand is pushing with the equal force of the wall is pushing back on the box by the hand. Everything is equal. Nothing is moving. So all of these are equal. Okay, these are our force pairs, our second law force pairs. The friction and the Earth, the hand and the wall. That is our force diagram and the picture. So earlier I had said, so I like the way this looks, this is right, and the way I had defined it earlier was correct too, but there's a better way for me to write this because it's not the coefficient of static friction, which I defined there. So let's erase that, right? And we're just gonna say it is the force on the system, comma, by SW. The system and the wall. Does that make sense? It's the frictional force is what I'm saying. It's not just the coefficient of friction, it's the frictional force that is equivalent to that. That's what's keeping it up. That's the right information. So after I'm done drawing my picture, right, I need to be able to define a coordinate system so my picture works with it. So here we defined a y as 9.8 meters per second, right? It's like the force that's getting pulled down and stuff. So we're not going to draw a conventional coordinate system. We're going to flip it, right? So we're going to say it like this, and we're going to say y negative and y positive have switched places. And now we're going to leave our x's the same. So this is going to be subtraction. Whoop, and this is going to be the plus coordinate system. So that everything is getting positive. It's just going to make my math simpler, and that's just kind of the way I think. So we're going to use this coordinate system. Okay, so now that we've, done the concept, made assumptions, wrote down what we needed, drawn a picture, done all the steps before, this is where we're going to start doing physics. Alright, let's erase this. So the next step on the problem solving guideline after drawing a picture is to simply write down all, oops, that's a G, it needs to be a Q. And so our professor, or most professors, give you like an equation sheet to follow on when you're doing an exam or working with problems, or you can just look it up. So for this problem, I'm going to say equations that we need, of course, because this is a force pairs question, and to get long, let's just write it down. Earlier, we defined our sum of forces to equal 0 newtons, so of course we're going to need that. So we're going to do sum of forces is equal to M times A, right? Next, we're going to, there's another equation, and force is static friction, right? S is equal to mu s, right? There, times Fm. So force normal, which we saw earlier in my picture. Okay. So these are the two equations straight from the equation sheet that we're going to use. Okay. So before we can go in and start plugging stuff in, we need to solve our equation in variable form and end up with one equation. So we're going to do variable form. Right. So, because this is a force pairs question, there's a lot of stuff that we can set equal to each other. Remember how earlier I drew a bunch of lines and said they were equal? So this is where I'm going to actually define them, right? So let's say the force on a system by the wall is equal to the force on the system by the hand. And that's magnitude, so you're going to do the absolute value. So this magnitude is equal to this magnitude. Again, the system isn't moving, right? You're pushing on the wall's pushing back. It's equal, nothing's moving. We're also going to say that the force on the system by the earth and magnitude is equal to the force friction there. Because again, nothing's moving up and down, everything's stagnant. Okay. So earlier in the picture, I said that F sub W is equivalent to Fn. Right? So that's normal force. Okay. So that's what I said. Okay, what else do we know? We also know that the force on the system by the earth, right? So force, system, earth. Right? Our subscripts are very important in this case, is equal to the mass total, so M tot. Times G. So this is equivalent to this times this, right? Okay. I like that so far. Okay. So I moved the equations down here and rewrote everything that we solved for in the variable form, the first part of the variable form up there, just so I could have more space to work and solve this problem. Okay, so now I'm going to set a lot of things equal to each other, right? Because now we see some stuff in our equations and our inside the variable form earlier to each other, right? So now that we see a lot of things coming back. So here, right, we said FSE is equal to FS. Is there anywhere else that we see that? Down here, right, we see FS. So we can set this term equal to this term, right? So let's do that. So let this be like FSE is equal to mu S times Fn, right? So what is FSE, right? We have a term for it. So we're going to say M total times G is equal to mu S times Fn, right? And now, up here, right, we set Fn equal to F sub W. So the force on the system by the wall is our normal force. So I'm just gonna go here, I'm gonna erase that, right, and write F sub W, okay? So, in this, if we go back to earlier, we said what we needed was the force on the system by the hand, right? How much force in pounds, right? So, F sub W. Let's see. We can take a moment and figure this out. So here, right, we said F sub W is equal to F sub H. We can just put that there, right? So we're just setting a lot of things equal to each other. F sub H times U is equal to G times M total. Right? Okay, so now we're looking for this, right? So now it's just algebra. We're going to divide both sides by mu s. Let's just do that. So erase this underline. Mu s, boop, boop. And now we have F and H. Right? What we're looking for, set to S times mass total times G. Okay, now we have one equation. Okay, so now that we've done our long variable form, I have my calculator because it's time for us to finally solve for the force on the system by the hand. Right? So now we have our given information and our one variable form solved equation, right? We have one thing. Now it's just plugging each other, right? So we have mass total. So we're going to do 8, right? Mass 1 plus 4 for mass 2 times 9.8, which is positive because of how we defined our coordinate system earlier. All over, right? This is meters per second, don't forget. Those kilograms. Ooh. Yeah, don't forget you need your units. And then 0.8, which is units. Okay. So I already did that, put that in the calculator. I don't know if you can see. You can't just see now? Yeah, okay, cool. So now, right, we ended up, I'm gonna hit enter, with 147 Newton. So our answer is in Newton. And earlier, if you remember, we were looking for the force on the system by the hand in pounds. So we want to do that conversion. So the conversion is 1 Newton times 1 lbs over 4.448 newtons is equal to pounds. Right? You're going to put there and there. And so we're just going to do 140. Now we're going to do divided by 4.448. You get, so this is newtons, 4.48. And then you get 33. 0. L-E-S. If you remember earlier, the beginning of the problem, this is what we were looking for.